Sunday afternoon. Thanks for taking the time to come here. And Richard was very effusive. I have to say thanks, and thanks to Leap. I think he's been one of the best mentors I've had in my career. And actually, that makes a lot of difference for an engineer. And happy to be here with partnering with Leap. And thanks to Women Who Code also. I think it's a great pursuit of a noble cause and something that we really want to push, and happy to have people from them.
Can I interrupt for one thing? And if you can hold your question until the end, that will be great. Yeah, just want to give that comment.
Okay, yeah. Sounds good. So if you can't hear me in the end, tell me, I can be louder. What do we want to talk today? I want to talk about the Uber knowledge graph. What does it mean? And don't expect to walk away knowing how to build everything. It's too short a time for that. I think the intent is to understand what are the things that goes into building such a new infrastructure, just the key aspects, and just getting a taste of it at a broad level. In terms of how do you want to structure this talk, let's talk about what are graphs and how do they provide a new perspective on data, and what are the technical challenges in building it. Things to remember, non-technical things which are very critical to remember while building a product. And finally, let's have some fun looking at some cool graphs. So let's look at the Uber ecosystem. Uber has 3 lines of business. One is a ride-sharing business. The second is, which is doing actually very, very well. Uber Eats, which is an up-and-coming business doing fantastically well on exponential growth curve. And Uber Freight, I don't know how many of you have heard of Freight. This is the first B2B offering, which is quite nascent, but still on a very fast trajectory to growth. If you look at Uber, all 3 businesses that we are in are essentially marketplace platforms. It is about how do you provide a service on a platform and balance supply and demand on that platform. So if you take a ride-sharing business, drivers provide the service. Transportation is the actual service, and riders, like all of us who avail of that service. How do you do a match between the right drivers and riders and keep a constant balance of, healthy balance of supply and demand in the marketplace? Similarly with Eats, we order food online and food gets delivered. Similarly with Freight, I have containers to ship around. How do I get drivers to help me mobilize that inventory? Largely, if you see, that is how the Uber ecosystem is structured. Drivers who provide supply of services, the actual service, and then the riders who are the actual consumers of that service. In addition, there's a lot of auxiliary entities in our system, right? Payment instruments, identity verification instruments like your passports and driving licenses, your device identifiers in terms of how do you access your app that you use. And finally, closing the loop on it, right? Ratings, referrals, reviews, customer support, and how do you handle all of those incidents. This is largely the Uber ecosystem in a nutshell. It does look interesting, but if you look at it from a data perspective, it is not really unique if you look at it from a pure engineering perspective. And why do I say that? Let's look at the different companies around, right? What does Uber do? A driver provides a trip as a service to a rider. Take Gmail, for example. Many of you use Gmail. What does Gmail do? A sender sends an email to a recipient. Take Amazon, for example. It is an e-commerce platform. A seller sells a product to a consumer. And take Facebook. This example is a little different, but a person shares a status update with your friends. This is a genesis when you look at it from a data perspective. Gmail has a lot of other aspects that revolve around it in terms of how do you do spam detection, how do you organize emails, labels, filters, all that. If you take Amazon, for example, how do you do fast delivery, how do you do guaranteed delivery, reputation management, all of that comes around it, logistics management. Facebook is all about newsfeed, ranking, discovery, spam, and fake news detection. The products are different, but if you look at it from an engineering perspective, from a data perspective, it is all about entities and relationships. Entities that take an action, and relationships that are the actions themselves. The real difference is how do you represent the data, access, analyze, and present this data to the different consumers. Let's talk about how does a classical data architecture look like in any of these companies or any of these products. If you look at it, there's a standard stack many of you will be familiar with. There is always at the bottom a source of truth, a golden source of truth, which is typically an RDBMS solution, say MySQL as an example. It's ACID compliant, highly write optimized, the data is highly normalized, and very complex foreign key relationships as your business matures and becomes more complex. If any of you have written really complex SQL queries with 10, 15, 20 inner joins and left joins, yeah, you must be familiar with this. The other evolution is into a data lake. And this is where you enter into the world of Hadoop, where you have cheap storage. Hardware is becoming quite accessible nowadays, horizontally scalable, ideal for analytical workloads. And this is where you try to denormalize all the data, flatten it out for efficiency of analysis. And largely at the top, you have high-speed access layers, NoSQL databases, key value stores, or columnar access, caching potentially if you need it, base compliant and highly read optimized. This is a typical stack, a classic data architecture if you look at any company around. What people have done of late is started to take a new approach to this paradigm. Can we start looking at it differently? Can we start moving away from a tabular view of data with multiple joins around where the focus is on the entity itself and the joins are considered secondary? You don't really emphasize the relationship among the data. To a completely pivot it around to say, can we take a relationship-centered view of the data? Graphs have emerged as a very powerful technology over the past decade, I have to say. I think Google was one of the first to embark on, many of you must have heard of PageRank. It's one of the things that's used in search ranking, one of the early adopters of graph, and today it's quite ubiquitous among the big players. The interesting thing about graphs is if you really design your infrastructure and data model right, you can achieve index-free adjacency, which essentially means you never have to deal with joins, you never have to deal with secondary indices, you never have to deal with how do I guarantee replication to a secondary table and clones of data and things like that, which I said theoretically over here because you have to be very careful on a use case by use case basis, but it's theoretically possible. Makes your life a whole lot simpler. Talk about it in details in the coming slides. I wanted to do a brief call out to an open source graph platform, which I strongly believe in, and we have also adopted at Uber now. Apache Tinkerpop is a very, very good scalable open source graph computing framework. And Janus Graph is a new incarnation of a graph engine that is fully compatible with that framework. I won't talk about details over here, but do read up on them. These are very new kids on the block compared to other Apache technologies, but they are very, very powerful and show a lot of promise. Now let's talk a bit about technical challenges. Now that we briefly covered how does the Uber ecosystem look like, how does it map to other companies, and if you want to take a data-centric approach, what does it take to build a generic purpose graph? And in the midst, I'll take an example of how each of these steps we have tried to address at Uber without going into very specifics. The first problem to solve is the data model. You get your data model wrong, doesn't matter how good an infrastructure you build after that, you're not going to be optimized, you're not going to get the efficiency you need. So let's look at it here. I have drawn 4 different variations of a data model. If you look at quadrant 1, driver and rider are represented as vertices, trip is an edge. Second quadrant is a different view of that data. You can say a person can be a driver or a rider, so I'm going to represent a user as a vertex, trip as a vertex because trip is the entity around which all contact happens, and then drivers and riders are relationships between those, or edges between those vertices. The third quadrant, you represent all three as vertices, essentially. The fourth one, I'm not sure how many of you are familiar with this. It's a concept called as an hypergraph. All the three, usually a typical understanding is edges there's a start and an end, but edges can have multiple starts and multiple ends, and that's called a hyperedge. So that's what quadrant 4 shows. There is a single edge that has 3 endpoints. The typical question people ask is, what is the right data model? The answer is there is no right data model. It all depends on the use case you're trying to solve. And while you design a data model, don't just look at today's use cases. Try to forecast your use cases into the future, because you get it wrong, you'll not have the time to change it further down the line. At Uber, what did we do? We took a hybrid of the data model in quadrant 1 and quadrant 3. We have a mix of the two. And there are use cases for us to consider a trip as a vertex, to do deep analysis on trips, which is why we are adopting quadrant 3. We also adopt quadrant 1, where you want to give faster, fewer hops access between drivers and riders. It's okay to have a hybrid data model. You can have duplicates in the graph, which is not really that bad. It's all about how do you want to access that data. The second thing I want to talk about is, you got your model right. The next thing you want to do is get your storage right. Typically, graphs are stored in an adjacency list format. It's very similar to the big table NoSQL data format, essentially. If you guys are not familiar, I would strongly encourage you to read that. Big table is one of the most paradigm shifts in database computing in the last decade. The way it happens is, draw an equivalence to an MySQL table, if you may. There are rows and columns. Similarly, here you have rows, which are vertices, and you have columns, which are the different properties of that vertex and the different edges. Why is this different from any standard tabular structure? You can say an edge is same as a foreign key relationship. You can say properties are just additional properties that exist on the table. The interesting point is, if you see the representation below, the entire edge and property is not a foreign key relationship. It's actually embedded into the row itself. This is how you eliminate potentially joins when you have to talk about it. When in a typical normalized data structure, you have a foreign key, you have to join against that table, which could sit on another machine or another data center, and you have complex back and forth. By embedding the data right into the vertex itself, you get high-speed access to that data in a highly co-located fashion. This is a fundamentally, it's a small change from the looks of it, but it yields significant improvements in performance and efficiency gains. This is what is available as part of the open source Apache Tinkerpop solution. Unfortunately, this hasn't scaled that well for us. This was a V1 adoption. This hasn't scaled one, and we have slightly moved away towards a different storage format. This is a great storage format, don't get me wrong. The problem is everything is in a single place. If I have hundreds of thousands of types of vertices, hyper edges, and other things that come in, dynamically edges being added and deleted, properties being changed, this is great for reads. It is not great for writes. So what we end up doing is further partitioning some of these storages into different vertex type classes, edge type classes, and try to get better efficiency around it. It's something that we are experimenting with, but it has shown great promise. This new data structure that we are trying to move towards. And this is one thing you should realize. Data storage is at a more fundamental abstraction at a lower level. This is something that your client should never see. And if you have designed it right, it gives you all the flexibility to migrate and experiment with newer formats while keeping your clients completely agnostic at the top. Third one, key thing to remember, graphs can get really big. If you take the Uber graph itself, for example, we have hundreds of millions of drivers and riders. We have billions of trips, tens of billions of properties on each of these entities, and this is just scratching the surface. This is just talking about one line of business. if you have to start putting all of this content in, and that's a lot of storage, that's a lot of relationships that you need to manage. And there are two fundamental approaches in the industry today. One is vertical scaling, which is my entire graph will fit on one machine. I will throw terabytes and terabytes of disk and memory capacity on that machine, but I'll keep it co-located to one machine. I don't want to take a distributed systems approach. It has its own wins. People usually are dismissive quite quickly, saying, hey, it's not distributed, but honestly, it has a lot of efficiency and performance gains. If you're really dealing with small to intermediate graph solutions, that's an ideal solution. But if you're really talking about graphs of the scale of Uber or Google or Facebook, I think our desire has been to go more distributed and look at the horizontal scaling aspect. How do you span your graph across multiple machines, across multiple shards? And this is where partitioning is a really, really hard problem. Because when you say, look me up, tell me who are my friends and their friends, it seems a very simple query, friend of friends, how hard can it be? But if every one of my friends is on a different machine and every one of their friends is on a different machine, you're talking about running requests across hundreds of machines, and you'll have to complete that request in less than a few tens of milliseconds. Not that easy to do that. This is where the smartness comes, is how do you collocate data? How do you predict what access patterns or what usage patterns will come in and bring those data points together on a single machine? The ones in red that are marked here are things that you preemptively know are going to span boundaries, and that's a risk you take. Maybe they are not high frequent traversals, or maybe you have enough time, latency to deal with those queries. So this is an art to an extent, I would say, partitioning of data. It is not even a science in many cases. A lot of it comes through trial and error. Let's go through another interesting problem called data segmentation. Everyone has probably experienced MapReduces and network graphs and whatnot. The Justin Bieber problem, or however you want to call it, the Kim Kardashian problem, or whatever it is called, it's essentially there are hotspots in every data that you look at. If Justin Bieber posts a photo on Instagram today, there are a few million followers and there are a few tens of millions of likes. You or me are not going to get to that scale. Now, if we are treated as equal cousins in the graph infrastructure, it's not probably going to be efficient. Now, how do you deal with that? And I think this is where there are many ways of tackling this. You can give Justin Bieber different personas. You can break the data geographically and try to segment the data. Those are all nice approaches. But the simplest, a very elegant solution that is followed in the community is known as the notion of supernode. Instead of using a vertex, use a super vertex. What does that mean? If you take the first graph, for example, over here, you see Justin Bieber in the center and all the edges pointing towards it. Let's say for some partitioning algorithm, everything in blue is considered one family, everything in orange is another, and green is another. So if you partition it across machines, this is the kind of partitions you end up with. And if that ends up being Justin Bieber with a few tens of millions, that machine is your hotspot. How do you solve that? You can be smart enough by changing the partitioning of a few edges. If you look at that very similar graph on the other side, the edges have been differently colored. We assigned a different partitioning logic. So they get evenly distributed across machines. Seems straightforward to do. Why don't we do this always? And this is where you realize what you trade off in terms of storage complexity comes back to you as query time complexity. Here, if you need to know all of Justin Bieber's friends, you know that in real time you just need to hit one machine. On the other side, you need to hit all three machines to find out who are his real friends. So what you do in this case is try to alleviate storage time hotspots with query time complexity constraints. And given that there are not going to be many Justin Biebers, and if they are also happen to exist, their data is also so frequently accessed and cached that the actual pressure on your database in terms of querying is going to be far lower. And that is why this is a very good trade-off to pursue. Having said that, this is not a trade-off we are readily pursuing at Uber yet, not because it's not a good optimization, it's a great optimization, because our data and use cases don't fit into this paradigm. I said Justin Biebers are rare. In our case, every driver takes tens of trips a day, which translates to thousands of trips in a year. And if you talk about millions of drivers, we suddenly have millions and millions of Justin Biebers in our network. So you can't start converting everything into a supernode. It just hurts your query time complexity. But the beauty for us is, if you look at the data, all the trips that a person takes have one thing in common. They are temporally distributed. They are distributed across the entire 12 months, 6 months window. So what we instead choose to pursue is do time segmentation of the edges. If you need to look at 6 months of data or 12 months of data, you can start segmenting that edges. So you don't need at any one point to look at Justin Bieber and all the edges around at a single time. Let me talk about the next problem that you face. Again, I'm not going deep into these problems. I'm making you broadly aware of the key problems to look at so you can pursue them further if that's of interest to you. The next problem is on data processing. Graph is a big buzzword in the industry, and people think graph is a one-stop shop, similar to machine learning. I'm doing machine learning, all my problems are solved. Unfortunately, no. Same is the problem with graphs. Deploying a graph doesn't solve all your problems magically. There are different use cases, different solutions and infrastructures you need to build for each and every one of them. The two key ways graphs are used today is an online transaction processing and analytics engine. What's the difference between the two? The first one is essentially start at a node and traverse the neighborhood of that node. So this is essentially saying, tell me who are all Richard's friends. So you start with Richard as a node in the graph and then traverse the localized region around Richard to find out the data. Or you can say friends of friends of friends of Richard, for example. That's a 3-hop query that you take in the localized neighborhood as a graph. That's a whole different area of graph infrastructure which has to be heavily optimized for real-time queries, point queries, random access queries. The other is an analytics engine, which anyone from the data warehousing community might be more familiar with. This is essentially saying, tell me everyone's friends. How many friends, say, what's the average number of friends does a person have if you run that kind of a query? You want to start with every vertex in the graph, compute all of their friends, do a count on it, and then do an average on it. So that is similar to a MapReduce kind of a query for you, an offline batch query with sequential data access potentially. BSP is another interesting style. It's called batch synchronous processing. It's an interesting style of analytics workload. Consider that as true parallel computing on a distributed systems infrastructure. What that means is, to put it in layman's terms, run a MapReduce across all the nodes, share all that information with all the other edges so that intelligence is available. Then run a MapReduce all over it again. Then synchronize all your results. Then run other series of MapReduces. An example of that. Doesn't seem like a good use of time. Why would I do it that way? If you take the Google PageRank algorithm, for example, billions and billions of pages, trillions of links, how do you compute the relative score? It is very difficult for any web page to look at the entire graph in the entire web of links in the world to actually compute any search quality metrics. What you essentially do is run a MapReduce in a small neighborhood. Let me just look at my neighbors and run one round of computation. Then I'm going to share the results of my computation with all my neighbors. Then I run another round of computation where that information is further propagated to the second hop and then to the third hop. And this is called localized computing in a graph framework. And there's some of the very powerful algorithms that you can run, like running PageRank at trillions of nodes and edges scale is not easy to pull off, and this runs like a charm, essentially. The next thing is data access. You have all this data, you have modeled it, you have stored it, you have partitioned it, you have done all smart things with it. How are you going to access this data? Let's take a simple example. Take LinkedIn, for example, right? A social graph. Let's say I'm Alice. I know there is a person, Bob, who exists, and I need to get in touch with Bob. I need to find out who can refer me to Bob. I don't know if it is my direct friend or my friend of my friend, or is it 7 hops away? I don't know. How do you typically, like, let's say if that were an interview question, how do you typically find the shortest path in a graph? If you have to write code, most people end up writing Dijkstra's algorithm, few tens of thousands of lines of code, or however you do it. Think of it if you want to do it in the SQL realm. Honestly, I don't even know if you can do it in SQL. Maybe there is a very smart recipe to do it. I'm not aware of it. Graphs provide a very, very interesting way of solving that problem. And this is where Gremlin is very similar to SQL, but completely different in paradigm. It is not a procedural execution engine. It's more a data flow and a functional language. So if you take an example, you essentially say g.v, which means start with a graph G, look at all the vertices. Now search all the vertices for the name Alice, which essentially means I've reached the vertex Alice. Now, from there, I want to compute a simple path, direct path to another person. And I'm going to keep doing this one-hop query repeatedly till I've reached another vertex called Bob. And once I've reached it, then I'm going to emit what the shortest path between those two are. Maybe it's 3 hops, and these are the 3 people who can help me get in touch. A simple one-line query that helps you solve this problem. You don't have to work on really complex code or multiple, like think of how you do this using inner joins or left joins in SQL, right? If you want to do a multi-deep hop analysis traversal of the graph. Gremlin is even smart enough to say you can define your own functions. You can define your own function called shortest path, which can be representative of the one above, but it can also have additional logic to say, you know what, if I've seen this link too often, just eliminate this. Or maybe this is a link that is not very common. How many friends do you have on LinkedIn and Facebook that you probably don't even remember why they are in your network or when you added them? So can I purge out those edges? Those are things you can additionally fold in. You can go towards even really complex functions which actually make your customers' lives easier. What if someone can write a query to say, g.user_Alice, find friend Bob? And the entire logic can be combined into such a simple predicate. This is the power in terms of, this opens up access to everyone in the domain around you. Nothing stops a customer support person today from running this query. You don't need to understand what a graph is. You just need to understand these key functions in terms of how they work. And this opens up a whole bunch of doors for analysis. Now, moving on a bit, going beyond technology, right? I think I covered a few aspects of data at a broad level. Working on engineering problems alone does not solve or make a product successful. All companies we work with are commercial for-profit entities. We are not in a research lab. So it's a whole different approach, essentially, in terms of how do you bring a product to market. The first thing is, think about your planning horizon. There was a recent review I read on, a quote I read on Harvard Business Review. It was a great article. It essentially says, the most important thing that helps keeps people's motivation at work every day is getting those small wins when they're working on meaningful projects. Nothing else matters. And it's a very powerful quote. And I think that's something that every tech lead or manager or anyone or product manager who's building a product should realize. Don't try to tackle all problems at once. I mentioned 7 or 8 engineering problems that you can solve as part of graph. If we try to solve all that, it'll take us 3 years to build the graph. And probably all the use cases would have been addressed in other ways by then. or probably those use cases may not even exist by then. Try to launch and iterate, deliver incremental value, and most importantly, it helps you learn from your mistakes. For example, a complex decision we even today face is, I talked about that storage representation, whether it's a big table format that we are not too happy with. We shipped our V1 with that storage format, knowing that it's not ideal for us, because we had to get something out the door to make sure it actually works for our customers. And now in V2, we decided, okay, we'll take a stab at fixing it. Another interesting thing is whether the data is stored in disk or in memory. Because you put all of these graph data on disk, there is a spindle hit limit that you have. You can't go faster than that. It's easy to put it in memory. But the open source technologies that exist are compatible with disk-based storage systems. They are not compatible with memory-based storage systems as of today. So we can take something off the shelf and leverage it and help us move faster rather than try to reinvent the wheel on how to make it optimal. And we have punted it out a good into V3 or V4 for us. It's an important win, but not right now. It's always important to have the long-term roadmap peppered with small wins along the way, short-term deliverables. The long-term roadmap is important because you need to be sure that you don't get deviated. It's always easy when you run on a big project to get deviated, and then you look back 6 months later, you're in a completely different North Star that you're chasing. The long-term plan helps you keep that pivot for you. And yeah, it keeps the morale of people high if you keep delivering these quick wins. And we just made this t-shirt last week when we delivered V2. So it's a great checkpoint for the entire team. Second is resource planning. This is not easy to get right at all. And what people end up doing is try to avoid it. Please don't do that. This is a very important thing. Never skip the prototyping phase. And this is where I like the quote from Donald Rumsfeld. It was not the ideal context that the quote was mentioned in, but it's a very powerful and important context. There are known knowns, and these are known knowns are the problems that I talked about before this. The different issues around data partitioning, segmentation. There are known unknowns which I don't even know. There are a few things, like I talked about memory versus disk. I don't know if we can do a memory-based system. We'll have to try it out. I know that it's a problem, but I don't know if it can be fixed. And there are unknown unknowns. One of you could be telling me that you totally missed this one, and I'll be like, okay, that's possible. You'll need to budget for that. You'll need to budget for every one of these corner cases. And look to always leverage what exists already. I think one of the big things I was really proud of my team is they jumped immediately around to say, what's available in the market? What can we leverage? Who are those people have this technology if we can potentially license? Is there anything in the open source world? Get a jump start. Don't try to reinvent the wheel. It just doesn't solve anyone's purpose. Finally, when people talk about resource planning, it's always about dollars. It's always about machines. It's always about time. How do I get my Gantt chart right? Engineers are your biggest resources, and that is the key thing. How do you get the smart engineer? How do you get them motivated? And to talk about that at length also, I think this was something that we followed at Uber is, I call it the three-stage philosophy, right? You need to believe in the mission, you need to adopt it, and then you need to excel in the pursuit of it. Uber is a high-growth company, and similar to Facebook was a few years ago and Google before that. During that growth hacking phase, everyone is so optimized in terms of focused on getting quick wins out the door and really moving the needle on the business. Talking to such an engineer and convincing them to say, you need to make a long-term bet on an infrastructure that is on a multi-year horizon is not easy. And how do you change that mindset? How do you first prove to them that there is a need for this technology and that it can have exponential impact in the years to come? The second is, once you make them believe, you need to have them adopt this. Believing is one thing, but then actually adopting and following through on it. You need to eliminate the fear of failure, because what if it fails 6 months later? Is my career going to be hurt? Is my promotion going to be hurt? These are common things that most managers would hear. How do you give them a safe environment where they have the time to learn the new skills that they may not have and also pursue risky bets, knowing that they will be well rewarded for that? And finally, once you create that environment, that's when you start to get excellent results from them. Right? Let their creative juices follow, put them into a shelter where there's no distractions, and support whatever creative ideas come from them. And when I talked about the storage format, that was one of the engineers on my team who came in and said, this is something that's been used in the open source for the last 3 years. I don't think it's right. I want to pursue a different one. It's scary for a manager when someone comes and says, I want to change the guts of the system. But that's something that you need to encourage. It takes time for people to get to that stage, and you need to pursue that and encourage them in that pursuit forward. Finally, how do you take this to executives? Uber at this point is on an extremely fast exponential growth curve, but you're not profitable at this point. We are converging towards that, but the pinch you find when you're making losses on a daily basis is pretty strong. How do you make a case to them? How do you get your executives to believe that this can be a game changer? Convince them that there is delayed ROI on this, but it could be exponential that it pays off. And once they're on board, this is where you need the constant periodic wins. You need to show the small wins for them to believe that you're headed in the right direction. You know what you're doing. And the opportunity cost that you have lost with all those engineers working on this rather than other initiatives, can you offset that opportunity cost steadily with these quick wins? That's fundamental to keeping your project on a steady track. And finally, I think, how do you guide forward? I think the important thing that happens is when suddenly people see quick wins, people try to pounce on it to say, let's do 25 other things. And I think this is where you need to balance to essentially say, early wins are great, but they need the time to bake in. And stick to your original plan. It's okay to deviate a bit, but not significantly. There's a reason you created that long-term roadmap. And this is a constant handshake that you as a team lead or a manager or an executive need to run with people, the engineers that report to you or to your bosses above you. And if you don't get that handshake right, projects don't succeed. Technology doesn't make it work. It's people that make projects work. Finally, I think I've spoken enough. Graphs are at the end of the day quite colorful, and let me just walk you through a few illustrations. And fortunately, I can't walk you through any actual examples of how graph is used at Uber for obvious reasons. So I've tried to create a few illustrative examples that can give you an idea. Let's take the first example. Let's talk about how graphs can be used in the context of fraud. Let's say, how do you do identity theft detection? Take an example. The node in the center is a driver. He was referred to by another driver. And quickly you can see there's something suspicious here. He has 39 credit cards. He has 17 devices associated with his account. Something seems fishy. You cannot obviously say it's wrong because there are many countries in the world that offer one-time credit cards that you can swap out for security reasons. So probably there's a valid reason for having 39 cards. 17 devices, I'll still find it hard to explain, but maybe there is a reason that exists. So let's do further investigation, right? Let's see who's the person who referred this guy. Maybe if it is a really good person, maybe this is a legitimate use case. Let's look at the person who referred him. Okay, that's suspicious too again. He has 48 credit cards and 16 devices. And the biggest red flag, I don't know if you guys have noticed, both the referrer and the referee not just have the referral relationship between them, they also have a device that is shared in common. And this is where shortest path becomes important. How common is it that you recommend another person and you end up using the same phone as them? Maybe it's your family member, which is a legitimate use case, or you just created a fake account, or you stole someone else's account and put it on your phone. And these help us give us a lot of deep insights and actually to expand on. And if you want to dig deeper, I think the next stage of investigation typically is, let's figure out what those devices actually try to do. And if you dig deeper, you can start to analyze each of these devices and further expand on in an iterative fashion. Similarly, look at the number of credit cards. This view tells you there's something really seriously wrong. Let's talk about another example similarly. Again, ignore the case that he has 242 credit cards and 6 devices. That's something we discussed before, but let's look at the referral in this case. This guy was referred by another person. Let's dig deeper and find out who the referrer is. And that person has referred so many people in the network. And the ones in red are people that in past investigations we have found to be suspicious. If you see something hidden over there, there is a blue person with number 872. Those are the number of people he has additionally referred. So this person has referred a few thousands of people. Now, you could be Justin Bieber, but I don't think no one ever refers that many people. So this is a clear case of incentive abuse, right? Today, if you refer a person, you get some discounts. If you're a driver, you get $1,000 discount bonus. If you're a rider, you get, I think, $10, $15. I don't know the exact numbers. But that's a lot of money to make. This is a classic case of incentive abuse for us. So graphs are very powerful in terms of investigation for us. If you were to do this in a tabular format, think of how difficult that would be. You talked about the structure of graphs. Let's talk about a slightly different analysis on top of the graphs. Let's take an example of social influence, right? What is this graph? This is the referral graph. Every person who has referred all their friends into the network. Here I'm assuming every referral is a valid referral for simplicity. And I've tried to, again, these are fake numbers, so I tried to annotate each node with saying how much money did they spend on Uber, paying for a trip or paying for a restaurant order or something. If you see the node at the center, he spent $0. It's very easy for us to say, this is not an active user for us, this is not a big user who can contribute very high lifetime value to us. I would beg to differ. I would say that is your VIP customer, because that guy has managed single-handedly to refer all these people who in turn refer all the other people who spend so much money on our network. If we didn't have this guy, all of the other players may not have materialized on our network. This is a very important thing that we need to take into account. Typically, we don't get easy analytics to do some of this information. Now, is it possible to do this using traditional means? Yes, it is. Is it much simpler to do it on a graph? Yes, it is. Like I said, it's a one-line gremlin query that you write, and you can do a lot of complex analysis on network centrality and click detection and whatnot. The last one I'll talk about is an even more abstract topic. This is some sample data. I was just analyzing it while, so I thought I'll just capture it here. Uber Eats, people order Uber Eats all the time, lots of orders that come in. I tried to map out the different cuisines that people look at, that they order, and the affinity towards different cuisines. So basically, if you see a person who orders Indian food, which is the green, typically orders Indian food and only Indian food. If you show them a Japanese restaurant or a burger shop as recommendations, probably they're not going to go for it. If you look at Chinese or a Japanese consumer, again, they go for that cuisine. They don't go for any other cuisine. The other in this case, I didn't get to, it's American cuisine essentially. But if you look at Italian, people who order Italian are equally likely to order Thai and Mexican food. Why? I don't know. It's not our job to interpret that. It's our job to adapt to that information. That is the social behavior. Now, can we adapt our recommendations based on this? And this is very powerful. This is a one-line collaborative filtering algorithm, a query that you can run on the graph, analyze millions of orders, and come up with this kind of an analysis. Graphs can be powerful. You can also, I'll end with one caveat. There's lots and lots of data in the world. It's about how you interpret that data. You can reach all kinds of wrong conclusions with data by taking skewed observations. So you need to be objective when you look at it, and you need to be thoroughly verifying your data. Don't get into the trap of a selective data set. Thank you.